So Pranjal would be talking about his dissertation, which is titled as A Tale of Hardness, De-Randomization and Debordering in Complexity Theory. I'll just introduce Pranjal. He is currently a postdoc at School of Computing NUS, working with Professor Devesh Agarwal. His broad research area is complexity theory. In particular, he works on algebraic complexity theory, geometric complexity, and distribution testing. He finished his PhD in computer science from CMI under the guidance of Professor Nitin Saxena. During his PhD, he was supported by the Google PhD Fellowship. He obtained his bachelor's and master's both in mathematics and computer science, both from CMI. So let's welcome the first speaker of the session with a huge round of applause, please.
Okay. Thank you. Thank you everyone for coming. So the title of the talk is Tale of Hardness, De-Randomization and Debordering in Complexity Theory, which is the title of my thesis. But I'll try to squeeze some of the parts of my thesis into a 20-minute talk. So it will probably be a micro story rather than a tale, but I'll try to convince you that some of the results are interesting and worth further investigation. Okay. So let me start with something called determinant versus permanent. So Nutan gave a talk yesterday on basics of algebraic complexity, where she introduced some of the basic stuff. And today morning, Neeraj also gave a nice talk on the application of algebraic complexity in machine learning. But what I'll do today in this talk will be a slightly different perspective, computational perspective on algebraic complexity. So let's start. So as we all know, P not equal to NP is basically the holy grail, the main question in computer science, which we'd like to solve. And so the question is basically whether verification is easier than finding a solution. And the conjecture says that yes, probably it is true, you can verify easily, but finding the solution should be harder. And there have been some barrier results known. By barrier, it means that there are results where they say that, look, we have been trying to prove P not equal to NP via different proof systems and proof strategies, but many of them will not work. Even if they are proving some mild lower bounds, it will not lead to solving P not equal to NP. And one of the main interesting results were due to Rajvarv and Rudich back 30 years back, where they introduced what is called a natural proof. And natural proof is basically, you can think of are all the proofs which is very natural in some sense. I'm not going into the definition. So they said that, okay, most of the lower bounds that we have been trying are natural and they will never lead to proof P not equal to NP. And that was actually a very heartbreaking situation that time, because people merely knew other techniques which could actually lead to P not equal to NP. And so one of the techniques, one of the very few techniques which is known, which could potentially break that barrier, is called the geometric complexity theory, which I work in, and I'll try to describe the basics, the very basic fundamentals of this program. And also, before going into other details, please feel free to interrupt and ask any questions. Okay, so so what is GCT? So in 2001, Mulmule and Soni, they proposed this program GCT1, and they said that, look, we will try to understand some of the algebraic P not equal to NP questions, which is called the VP not equal to NP questions, have been already defined before, or the determinant versus permanent questions, which I'll define in this talk. So they said, look, study these problems, but study these problems in a slightly different way, which is called the algebraic approximations, or what they call it, border complexity. And they said that, look, if we can study and understand some basic properties of these two objects that we'll define in the next slide, first, they would probably lead to P not equal to NP, and second, that the proof strategy that we are giving is not natural. So it actually breaks the barrier. Good. So we would like to understand what is the determinant versus permanent question, and what we mean by algebraic approximations or border complexity. Okay. So the main object will be a matrix. So here is a matrix where there are like n cross n, I don't know. Okay. Yeah. So n cross n matrix where each entries are some variables xij. So now I'll just assume high school algebra and high school analysis, nothing more in this talk. Okay. So remember the usual determinant definition. It's basically you have an n cross n matrix and you are expanding it term by term, like one entry, another entry, and so on and so forth. So this will actually give some polynomial in n square variable in degree n. This is called the usual determinant. That's a basic high school determinant. And there is another polynomial called the permanent polynomial, which is almost similar to determinant but without a plus minus, because if you remember, when you are expanding determinant, there is a plus and there is a minus depending on the rows and columns. For the permanent, there is no minus. All things are positive. And you would be surprised to know that actually in this era of learning, so you want to actually learn it. So you have some distribution you want to understand, you want to learn, and you want to eventually understand how close they are or how good they are, the learning algorithms, right? And you would be, so most of the cases you can show that the distance, how good or bad this learned data or learned distributions are actually can be captured by permanent polynomial. Okay, I'll not go into that, but if you like to discuss, I'll be happy to do after the talk. And just to give you an example, so this is a determinant of 2 cross 2 where there is this minus x11, x22, minus x12, x21, but the permanent there is no minus, all is plus. Okay. So what is the determinant versus permanent question? So to do that, let's just call it linear polynomial. I call L a linear polynomial where the degree is 1, okay, at most 1. For example, this 2xx1, 2x11 plus 5x32 plus 4. So constants are allowed like 4, but I'm not allowing any degree 2 or degree 3 and so on, just 1 in each variable. Okay. What is the permanent versus determinant question? Is this. I want to write the permanent polynomial, which I defined already, as determinant of some matrix where the entries are linear polynomials. L11, L12, LIS, these are all linear polynomials. So I have a polynomial permanent and I want to write determinant as a matrix, big matrix, where each entries are linear polynomials, like, as I said, like 2x11 plus blah, blah, like that. And the question is, what is the dimension, what is the minimum S that requires to write this permanent? That's all we are asking, okay? And variance conjecture basically says that S has to be really large. There is no way you can write permanent as a small determinant. Your S, the dimension of the matrix has to be really large. That is basically called the algebraic P not equal to NP question. So you could ask, and this is actually also the VV not equal to VNP question in which Nutan and Neeraj also talked about. So what is the scenario and why we are studying this? One of the implications is this: P not equal to NP implies this conjecture, and this conjecture actually implies P not equal to NP in some other model which is called the BSS model. So somehow this variance conjecture is squeezed between two P not equal to NP questions. That is why this is important. And but you could ask me the following question: that look, this seems to be an easier question, but why? I mean, variance conjecture may not actually lead to P not equal to NP. So why even studying this, right? So one of the things would be at least solve the easier question than before solving the P not equal to NP questions. But there are some more motivations which I already talked about. There's the breaking the barrier and so on and so forth, which I'll come in the next slide. That why this question is very fundamentally important. Okay. So till now I have been talking about lower bounds. But let me talk about some algorithmic question now, which is slightly different than what I was talking about, but these questions are related. So what is the PIT question? Now I am saying the same question. I have a determinant of a matrix. I want to test whether that polynomial determinant of A, where again the entries are linear polynomials, I want to check whether determinant of A is 0 or not. What could happen is that when you are expanding this n cross n when you are calculating, maybe things are getting cancelled, you don't know. But you cannot actually hope to exactly calculate everything because there are like 2 to the n many things. So it will take a lot of time. So you would ideally like to solve it very, very fast. So the question is, can you deterministically solve this question? This is called the PIT question. And what is known is that there is a very efficient randomized algorithm. If you use randomness, then you can solve this problem very easily. What you do is basically very basic. You basically have a polynomial and you randomly evaluate it to a point. Like basically you have some finite points, you basically pick randomly and evaluate it. If it is non-zero, the actual polynomial is non-zero. If it is 0, the actual polynomial is 0. But this requires randomness. So this is basically this y, this is in BPP. The question is, can we de-randomize? So can we remove the randomness from this? So this also tries to solve, there is a famous conjecture of BPP equal to P, where basically it says that all the problems that we can efficiently solve using randomness, can we actually de-randomize it? Meaning, can we remove the randomness with slight blow up of time complexity? Maybe I am solving a problem in 1 hour with randomness, maybe in 10 hours I want to solve that problem without randomness, but can we always do that? And it turns out that there are some special cases where this can be de-randomized, so you can actually remove the randomness. And what I was talking in the previous slide is that this question of efficient algorithm, this PIT is actually almost equivalent to solving determinant versus permanent. So previously I was talking about some lower bound question. This initially seemed to be an extremely different question, but suddenly this algorithm versus lower bound, there is a connection, and they are very strong in some sense. And also de-randomizing PIT has many algorithmic applications. For example, in graph theory, there are primality testing, and there are coding theory, and many different applications of this PIT. Okay. So now I'll talk about one of our first results. So I was talking about linear polynomials, right? Degree 1 polynomial. But instead of degree 1, let's just also allow constant degree polynomials. For example, this is a degree 2 polynomial. Because x1 squared, x32 squared, there are the degree 2. So this is a degree 2 polynomial or quadratic polynomial. Let's just use the same in the same model. So you have a determinant and you want to use this, instead of linear polynomials, you want to use quadratic polynomials. So for example, if you look at this determinant, this is very specific determinants where, let's say, Fij's are constant degree polynomials. You look at the very specific determinant where there is this diagonal and upper diagonal, and only this, there is F2s in this. So this way you can actually calculate the product plus product. So F11 dot F1s plus F21 dot F2s. You can ask the same question that can we actually do PIT for this model? This seems to be a very specific question, right? Because initially I was talking about very generic determinants, but now I'm talking about very specific structure of that. The question is, can we do PIT for this? And more generally, can we do, instead of sum of two products, can I do for constant many products? And this was open for a long time, and 3 years back, we actually solved it. We gave a deterministic algorithm in n to the log n time, so quasi-polynomial time. We could not solve it in polynomial time, but we almost did it, so we removed the randomness for this specific model. Okay, so this is the PIT result. I have not talked about approximation yet. The question, as I started with, can we do better using approximation? And what do you mean by that? So let's say initially I was allowing, let's say, 2x11 plus 3x22 plus blah blah blah. But now introduce a parameter epsilon, and think of this as some parameter which we will talk about later. But for now, epsilon is just a parameter. For example, the coefficients are of the form 1 by epsilon or 2 plus epsilon and so on and so forth. So these are linear polynomials in x11 and x21 and so on and so forth. But the coefficients are only in epsilon or 1 by epsilon. Okay. So now I ask the same question that I started with, but now I am allowing a limit. So what I am saying is, can I write permanent as determinant of a matrix in the limiting sense? What do we mean? That can I write permanent the polynomial as determinant of this S cross S matrix where these are linear entries, but the coefficients I am allowing some epsilon and so on and so forth, and now I am taking the limit. So the question is, can approximation do better in this? Maybe it does, maybe it does not, but the question is, can it? And this is actually the Mulmule-Sohony conjecture that I first talked about, the GCT program. This basically says that, look, even with limit also, even if you allow approximation, there is no way you can do better. So forget about without limit, even with limit also you cannot do better. That's the Mulmule-Sohony conjecture, or the geometric p-not-equal to NP question. And as probably you understand that this conjecture is actually much stronger than Valiant's conjecture, because Valiant saying that write it without limit. Mulmule-Sohony saying that please write it with limit. So if you cannot write without limit, there is no way that you can write it with limit. So this implies the Valiant's conjecture. So GCT, the program that I talked about, this resolves around these questions only. And how does it break the barrier that I talked about? So these two polynomials that I have been talking about, determinant and permanent, they have nice symmetries. I will not define what are the symmetries and for at least determinant and permanent, but they have some nice symmetries. and most of the polynomials do not have nice symmetries. So, a natural proof actually should work for many polynomials, but it says that it cannot be natural because otherwise most of the polynomials must have nice symmetries, which it does not. So that's why this actually breaks the barrier, and so probably this way you can solve this question. So this is the last which I call the sorry. So yeah, so I have talked about border or GCT. I have talked about the PIT. Now I'll just quickly go to the debordering. What do we mean by that? So Kumar, 3-4 years back, he showed a very interesting result. He said that, look, so if you remember, I was saying that f11 dot f1s plus sum of two products, right? So Kumar showed that any polynomial f can be written as limit of such polynomials. Even forget about constant degree, linear polynomials are enough. So any polynomial f can be written as limit of L11 dot L1s plus L21 dot L2s, where Li's are linear polynomials, but your s has to be large. Okay, so in terms of determinant, let me write it this way. So I have a very specific determinant, and any polynomial f can be written in this limiting, in the limiting sense. And I also should mention that without limit, you can never write it as sum of two products. Okay, so limit actually is really important. Okay, so this has connections to matrix multiplication algorithm and so on and so forth. And the question was, can we write f without limit? Like with limit we can write, but without limit can we? And we actually showed that we can actually write. This was another result in my thesis where we showed that, okay, the matrix, so if S, without limit also we can write it as a small determinant, but with poly S time. How much time to do? Okay, so I'll just finish. And one can show that the same result holds when the fan-in is, instead of 2, I can, if I allow k many, like constant, like 3, 4, and so on and so forth. Okay, so let me not go into the lower bound. So I don't have any time, right? Is it? Okay, so let me finish the, this is the last slide, okay. Yeah, so the conclusion is that, as I started with, can I do PI? So as we showed quasi-polynomial time PIT for the sum of product of constant degree polynomials. Can we do it in polynomial time? The second question is, can we understand the limit where I allow the Fij's to be constant degree? We could also only solve sum of products where Lij's are degree 1 polynomials, linear polynomials. We don't even understand what happens when the degree is 2. So that's it. That's what I wanted to say. Yeah, thank you.